So today's lesson, we're going to talk about applications of sinusoidal functions. So we've talked about this quite a bit. Now we're going to just let it run, that type of thing. So the idea here is to apply properties of sinusoidal functions, the amplitude, the period, the phase shift, and the equation of axis to sketch the graph, to determine equations, and to solve problems. That's the goal. So all these examples that we're going to look at today are visible in today's society. If you've ever gone to the east or west coast or to different countries close to oceans, we have cycles that deal with tides. So tide cycles run from a high tide to low tide, that type of thing. So the Bay of Fundy, all right, in tides, those are some of the biggest tidal fluctuations in around the world. If you ever get a chance to, it's worth going. And I'm going to tell you that the height of the tide is represented by this function, where x is the number of hours, and h of x is the height in the tides, and that's going to be in meters. I forgot to add that in there. Okay? So if we look at this, we can answer questions based on that function. All right? Determine the time it takes for one cycle to appear, just while you're thinking. Well, we know the period tells us the time for one cycle. And we know from the question that that is 2 pi over k. Well, our k here is pi over 6. All right, and then I can do the reciprocal and multiply. So in this case, 12 hours is the time it takes to make one cycle. Okay? Nothing too crazy. It says, determine the height of the water at high tide and low tide. How do you know? Well, that comes from our equation of axis. Well, if I'm looking at that, all right, well, my equation of axis here is 0. There's no vertical shift, all right? And I know my amplitude is 6.5. So we know that our maximum height is 0 plus 6.5. And our minimum height is 0 minus 6.5. Now you're asking yourself, that really makes no sense. But the idea there is, if you were looking at one point within the spot, the tide is running out, so you get a lot of water that's decreasing, and it's kind of factored into a spot somewhere near it, but basically it's drained off. That's how they know. But that's basically the idea of that. And now I can just sketch the graph. Well, the only other thing that I need to know about sketching the graph, what is my phase shift? Well, if I look at this, my basic function is sine x, and my phase shift is equal to 0. So that means it's not moving left or right. So I can look at this now. All right, I can, just like we did it in previous learning, all right, I can look at this and say, there's my max height, there's my minimum height, and I know my equation of axis is at 0. All right, and we know at the sine curve, it starts in the middle, right? We know that. Let's zoom out here. So that we know, if I'm looking at this, we're going to start at 0 there. All right, we also know that my period is 12 hours, so we know that we're going to end at 12 hours, and then I can figure out how far. Well, if I was looking at those through, that has to be in the middle of 0 and 12. We know that this graph is going to increase there, so half of 6 is 3. Between 3, 6, and 12 is 9. And we give that a go. So as you are going through this lesson, anytime that you need to push pause and go back to just allow you to sketch the graph, feel free to pause to plot the points. And I will give you some time prompts to actually plot the points as well. All right. So I'm going to go ahead and draw the next cycle. Next cycle goes from 12 to 24. In the middle is there. To continue the pattern is there. And there's my function. H of x equals 6.5 sine pi over 6x. Done. That would be that graph. All right, so tides are definitely a sinusoidal function. The idea there is high tide, low tide. We can give that a go. We have talked about Ferris wheels already. All right. Sometimes we don't know all the information, but we can figure out some things. Out of the Ferris wheel, a local fair has a radius of 7 meters, and the bottom of the Ferris wheel is 1.5 meters off the ground. Okay. It takes 32 seconds to make 2 revolutions. All right. So sometimes, and we're going to assume that the Ferris wheel starts at the minimum height. So when looking at this, what do you know? Well, I have a minimum height is 1.5 meters. So I know, looking at this, 1.5 meters it's about there. We also have a radius of 7 meters. Well, the radius of 7 meters tells us that halfway up our graph, we're going to be 7 meters. So we're actually going to be at my EOA, or at 7. So we're going to be at 8.5 meters. So I have to kind of troubleshoot what I know. And then at a max, I know that I'm going to be up another 7 meters, so 15.5 meters. So there's 15, 15.5. All right, perfect. So again, just like how we were doing before, I've got my equation maxes. I've got my information there for my max and my min. Okay, I have to look at my period. Well, my period is 32 seconds in 2 revolutions. That is 16 seconds. So I know that every 16 seconds, from 0 to 16, I got to get done. We also tells us that we are going to start at a minimum. So that means we're going to start there. 16 seconds later, it gets me there. Another 16 seconds gets me there. And then I can plot my points. So what I'm going to do is I'm going to push pause here. All right, and what I want you to do is plot that points for the first cycle, and then unpause it, and then come and check your answer. All right, so go ahead, push pause, and see what you get. So hopefully what you've done here is you recognize that half of 16 is 8 to get up to the max, and then half of 8 is 4. So I know that every 4 seconds I'm jumping over. All right, and I could do the same thing here. In the middle of 16 and 32 is 24. And then 4 seconds there, another 4 seconds there. And they're nice smooth curves, all right? And you get practice with it. There's my sketch, all right? Now, I gotta find out my equation. And we know all these things already. Our amplitude, my EOA, my period, and our phase shift. So now we're going to take that. Well, we know from up here, our EOA was 8.5 meters. That's from our graph. Our radius was 7 meters, because we know that's 7 meters down, 7 meters up. We know that our period is 16 seconds. So our value of K has to be 2 pi over the period. So that's 2 pi over 16, which is pi over 8. There's my value of K. And from here, I have to decide, am I going to use, what am I going to use my phase shift? Well, here are your 4 options. All right. So what I'm going to do is I'm going to hit pause again here. And what I'm going to ask you to do is, what would be the phase shift for each of these 4 functions? Write them down, and then tell me, and then come back and see, does it match up? So hopefully you wrote this down. For cos, it's going to start up at the maximum. So if I look at this, my maximum is at 8. That's why I picked 8. Sine starts in the middle and increases. So that's why I said 4. Negative cos, it starts out as minimum. So it could start at 0, or it could be at 16. Your choice, doesn't matter. And negative sine starts in the middle and goes down. That's at 12. So now I could just make my equations. So I'm going to do a couple here. For me, I like cos in this example because the max, the mins are nice. It doesn't matter. All right. So I'm gonna do that one. So my amplitude is, let's move it over here, 7 cos. My K value is pi over 8 x, or x minus 16, plus 8.5. And maybe I'll do the positive cos. Y equals 7 cos pi over 8, x minus 8, plus 8.5. And hopefully you've learned along the way is that the amplitude doesn't change, the period doesn't change, or the K value doesn't change, and the equation of action doesn't change. Both are perfectly fine. So many different answers. All right. If you've taken physics or taken a look at what a spring does, all right, it oscillates up and down. So think about like a little spring and it's bobbing up and down like a, I don't know, just a spring just bouncing up and down. And this is the graph it gets. The height of the spring over x is represented by h, and x is the time. So same idea. But maybe the concept of what we're doing is a little bit different. Determine the resting height of the spring when it's not oscillating. Interesting. So if I was looking at this, and I was looking at this grid, if this is not moving, it's at rest. So technically at rest, that's going to be my equation of axis. So I have to look at my